Okay, so welcome back to Homework 1, Part 3, where today we're going to investigating a vessel laid on its side, a cylindrical vessel laid on its side, and we have some liquid inside of it. Okay, and this liquid will exert some pressure forces on each face of the cylindrical vessel, as well as out the sidewall. Okay, so we're going to look at what the forces will look like. And you'll notice that I have a second diagram here. This is a profile view of our vessel. And I have a differential height, dH, defined. That is because pressure actually varies depending on how far below the surface of the liquid you are. So we define the surface of the liquid as 0, okay? And the H as how far down below the surface you are. So let's take a look at pressure. The most simple definition of pressure is force per unit area. So if we're looking at force, so force on the sidewalls has to equal pressure times A. What can we define pressure as? For a liquid, pressure is rho g h, right? Now what? Multiply by some differential area, right? Because we're looking at we're looking at a infinitesimally small wide slice, a little slice of the sidewall with a infinitesimally small height dH and what? L, the length of our vessel, right? So dA is actually equal to, so F side is equal to rho GH LDH. Okay, I expanded this dA out. This comes from dA. Okay. Now what? I should integrate this, right? Because I want to add up all of my slices together to get the resultant force of the sidewall. So let's go ahead and do that. We say that, well, what else do you notice? We have a bunch of constants, right? The only independent variable we have is h. Oh, one more thing. When you remember, this is the whole theme of today of the homework. So whenever you integrate, you always ask yourself the same question: what should be my bounds of integration? Well, if I'm looking to analyze the pressure forces below the surface of the liquid, I should start at 0 and go to some height below the surface of the liquid, right? And then that means that our h's here become dummy variables of integration. So now I can say that the force on the sidewall is equal to rho g times the length of the vessel into rho h dH. That's equal to, go ahead and integrate that. That's equal to 1/2 rho g L h squared. Okay? And there is our first expression. This is the far easier one. This is our first expression for one of the forces exerted on the vessel by the pressure of the liquid. Okay, let's get started. This is the harder part of the calculation. Finding the pressure force exerted on a particular face of this vessel. And it's harder because, well, as opposed to our previous calculation, where width of the differential area was constant, here, not so much. Width changes based on relative position. And it just so happens that this looks an awful lot like a unit circle, right? And it just so happens that this is particularly convenient to model this as theta, differential theta, okay, as a unit circle, because both width and height can easily be modeled by using trigonometry. So let's get on with that. Again, force of the face will be equal to pressure times area, where pressure is rho g h dA, differential area. For a differential area, you will notice that, well, in order for this to work, we'll have to split this into 2. So remember, don't let me forget, I have to multiply everything by 2 at the end. So let's take care of our h term. What is h equal? you notice that here, for here, this is r, radius, from the center. You'll notice that for some height, some additional height, well, that's equal to sine theta. So we can say that this is what? R plus r sine theta. Sine theta. Okay. Now what if we go below r? What if our theta is what? What if our theta is less than 0? If our theta is less than 0, well, it's very convenient because our sine term becomes negative. So now we will have r minus some height of this triangle, right? So some height of this triangle. So this is a rather convenient way to model our height. So we now say that the force of the face is equal to rho g h is r plus r sine theta. Let's split open our differential area term. How's differential area modeled? Yeah, see this triangle right here. Okay, dh, once again we have dh, differential height, multiplied by width. What's width? Well, width is very simply r cosine theta, right? It's the adjacent leg to your theta. So easy peasy. This is r cosine theta. But we have this dh here. Okay, you'll notice again, we are trying to integrate this, everything in terms of theta. So we want our differential height, to actually be a differential theta. So what do? Well, guess what? Calculus wasn't for nothing. We know h, we have an expression for h, so we can find th easy peasy. That's just the integral of our term for h. So now that's what? R cosine theta, right? So we have our f face. Remember, multiply everything by 2. What do I do that now? So don't forget. So 2 times rho g multiplied by r plus r sine theta times r cosine theta times r cosine theta is what? R squared cosine squared theta. Okay, and we're gonna have to wiggle this out. Okay, so now what? Now we should integrate everything, right? Should integrate everything to add up all of our little differential areas multiplied by its corresponding rho gh, right? And that's how I find my total sum of forces on a particular face of the vessel. And once we have an integral, we always should ask ourselves, what should my bounds of integration be? Call it theta 1 to theta 2. Okay? Because recall, I just realized I made a mistake. There should be a d theta here. And remember, when you integrate h, you have dh d theta. So really, dh should equal r cosine theta d theta. Okay? And that's how we get that expression right there. But what should our thetas be? What should our thetas be? Well, we're going from some angle theta, which corresponds to the height, the surface of the fluid, and we're integrating all the way to what? Negative 1/2 pi. So let's do the easy one first. So theta 2 is equal to negative pi over 2. But what about theta 1? Let's look at this. So for the initial height of the surface of the fluid, what do we have? It's going to be this leg. We're going to use the property of sine, SOHCAHTOA, right? So we're going to say that sine theta 1 is equal to opposite over hypotenuse. Well, the hypotenuse is r, radius. But what about this? What is that? Well, that is actually r minus h, right? The radius minus the height. Or sorry, rather, h minus r, the height. So this is the height minus the radius. See? h, and r. So if you subtract r from h, you're left with this little leg right there. So what does that tell us? That tells us that theta 1 is equal to the inverse sine of h minus r over r. So those are our bounds of integration. So let's go ahead and look at our integral now. See what we can massage out. We should really take out our constants, right? So 2 rho g. What else do we have? What else do we have? Well, you see here that we have a bunch of r's, right? So you can actually factor out an r cubed. Radius is constant. I just closed up my notebook. Hold on. Homework 1. There we go. Butterfingers. Okay, you can actually factor out an r cubed. That's rather convenient. R cubed. From theta 1 to theta 2. Okay, so now what do we have? We have cosine squared theta plus sine theta cosine squared theta d theta. Okay, so now what? We have an integral here. I bet you that integral looks very familiar to you. If you're watching this video, you've probably taken Calc 2 before, and I'm sure you saw plenty of these in Calc 2, right? You have to do integration by parts twice, something like that, to solve this integral by hand. But in the interest of time, and because this is not a Calc 2 class, I've cheated and used Wolfram Alpha. Okay, so I'm going ahead and cheat and copy down that solution for this integral for Wolfram Alpha. Okay, so now I say that my expression for force on a particular face is equal to twice rho g radius cubed. Okay, the expression 1/2 times theta plus sine theta cosine theta minus 1/3 cosine cubed theta evaluated from theta 2 to theta 1. So let's evaluate that at theta 2. Theta 2, recall, is negative pi over 2, and that's rather convenient because we have several cosine terms in here, and as you know, cosine of 1/2 or cosine of pi over 2 is always 0, so this goes away, that goes away. We're just left with this. So let's continue. So now the force on a particular face of our cylindrical vessel here is going to equal twice rho g r cubed multiplied by theta over 2 minus quantity. Now here we have an expression for sine, but we don't have one for cosine. We're going to want to substitute in cosine somehow, and the way we're going to do that is by using our friendly neighborhood trig identity, right? Sine squared theta plus excuse me, cosine squared theta is equal to 1. So if I'm looking for cosine, it's going to look something like this. Cosine theta 1 is equal to the radical 1 minus sine squared theta. Recall where sine theta is this, so I have, let's get rid of this, or give me some more room, where I have cosine, I'll keep this in red. So cosine theta 1 is equal to radical 1 minus h minus r squared over, excuse me, phone call, I did silence it, over what? Over r squared. Okay, we can simplify this a little. If we expand that out by FOIL, what do we have? H minus r, h minus r, h squared h squared minus 2hr, right? Plus r squared is that. Okay, so if I have, let's do a little math within math here. If I have r squared over r squared minus h squared minus 2hr minus r squared over r squared, well, then what? Then I have these cancel out. So my expression becomes cosine theta 1 is equal to radical h squared minus 2hr over r squared. Now I can simplify a little bit further by saying cosine theta 1 is equal to the radical h squared minus 2hr all over r. Okay, lots of algebra, but let's highlight this softly. This is my expression for cosine theta, and I'm gonna want to plug it into my evaluation for theta 1. Right, so let's get started. I have 1/2, or let's go ahead and distribute that through. Okay, theta 2 plus 1/2 sine cosine theta. What do I have? Sine cosine theta, so times the quantity radical h squared minus 2hr over r times what? Times, I'm trying to minimize the use of parentheses here, times h minus r over r. Okay, so that's this term taken care of. Now time to take care of this term. I have minus 1/3. So cosine cubed, what is that? Cubed, so now I have h negative 1/3 h squared minus 2hr radical over r, that whole quantity cubed. Okay, so let's rearrange my brackets to make sense. It's this whole expression here, so that minus this. Pretty nasty. I'm not going to simplify any further, but here is the finished derivation for the force exerted on a particular face of a cylindrical vessel laid on its side with some liquid in there. So, you know, just so we look back, that's how long this derivation took, and it's a one-liner, right? And that's how long the derivation for a face looks. A lot more complicated, but this is it. Okay, so this concludes part 3 of homework 1.